we wanted to capture some of those gradients as well. And then we had to actually find places to put them, and kind of our goal was to cover, mostly Baltimore, kind of within the 695 Beltway, outside around the city. And so this is our current network. We have 45 measurement sites around Baltimore. 4 of those are co-located at reference sites. We've been fortunate to be able to pair with the Maryland Department of the Environment and NIST. So we have co-locations for pollutants and greenhouse gases. And so we're using that data to help with our calibrations, and gives us kind of detailed reliability data on this low cost sensor. So you can see these co-locations with the blue triangles and the green dots are where we are. This is where the bridge collapsed. So we have a few sensors down in that area. One area that we're interested, as well as kind of, the beltway going around where trucks are maybe being routed, or perhaps crossing the city on some of the truck routes as well. So hopefully we're well positioned to be kind of looking at this this summer. All of these are connected through the wireless network, the cellular network, and so we can look at the sensors in real time. The sensors also have an SD card backup, which fortunately we're needing to use less and less as things have gotten more stable over the years. We have these field calibrations, and as Pete mentioned, we just recently deployed one more at the site where the mobile lab is parked. So that's giving us another set of comparison with kind of high quality measurements. So these are allowing us to look at cross sensitivities to other pollutants, environmental factors, and sensor drift. Some of these sensors have been up since 2018, so they're getting old in some cases. We've done a lot of work, as I mentioned, calibrating the PM 2.5 sensors. This is an example of that. These low-cost sensors in general are known to overestimate PM concentrations in the United States, particularly at high relative humidity conditions. So we've developed linear calibration models, as well as other machine learning and other approaches to be able to improve our estimation of the PM 2.5 and get to where we're within a couple micrograms per cubic meter of reference measurements. We've also looked at the sensor that's in the search monitor as a plant tower is the same sensor that's inside of Purple Air. So there's a huge number of Purple Airs around the country that have been deployed. The EPA has developed this pretty simple calibration approach for them. We've looked at that as well. You don't lose a lot by doing that. So we've been also kind of thinking about the trade-off between having the absolute best calibration for Baltimore versus just being able to compare our data nationally and with other cities that are putting up these kinds of networks, and being able to better engage with other communities that might be buying something like a Purple Air, or really lots of the commercially available devices are using the same plant tower sensor. So this is the new thing. So this is from last summer, the smoke event. You can see this is showing hourly data starting on June 5th. So a year ago today. And initially, the color bar here is on a log scale. So, as the colors go up, concentrations are getting a lot higher. And you can see these smoke plumes build in from kind of the north and the east, and then kind of swirling around and these are the highest concentrations. Our calibrated sensors around 200 micrograms per cubic meter at the worst conditions. Whether our calibrations work perfectly, 200 micrograms per cubic meter, I think is an open question. It's hard to calibrate something that you didn't have any trained data in that range. So, but I think, clearly the answer is very high. And so we're able to see some amount of this. There, you might notice that one side not sticking out, which is interesting. So I don't know if that RH sensor has magically healed itself or what, but this is where we are. I think that was all I had. So this is a big team of people who've been looking at it, well, going back to the search center and forward into, across BSEC, as well as a number of other studies that are trying to, as I mentioned yesterday, kind of use this data, also engage with the health aspects, both within BSEC and with other projects that are going on. So happy to take any questions.
Your time questions?
There.
So you see that some of these have been asked for a long time. So have you seen any drift like in the places where you have, I guess.
Yeah. So some of the sensors, we definitely have seen improvements by including just kind of linear time in the calibration model. Some of the sensors do an odd thing where they have like a dramatic baseline shift. They'll be like going along and go, "Whoop." And so what we've ended up doing is like treating those like they're different sensors and calibrating those independently because there's just this massive step change. Methane is one example, but a few of the sensors have done that. And then we found for the ozone monitor, that's the one where we're really like kind of losing the most data at this point in terms of we picked a sensor, it is no longer being manufactured, we can't replace it. And I'm not a huge fan of some of the alternatives, so we've just been kind of living with the data loss. I also think ozone probably doesn't vary on the same small spatial scale, so I'm just kind of living with that. Yeah.
Yeah, I'm just curious, like, would you mind elaborating a bit more about why like the sensor may have this kind of abrupt shift?
I don't know. There doesn't seem to be any like dramatic event that happens that precipitates that massive change in the sensor. So, and they don't all do it at the same time. It just seems to be a kind of random event. And not all the sensors do it, but some of them do.
Apologies if I missed it. You said you had it next to some of the NIST and
Mhm.
sites. Do you get pretty good agreement between the local?
The raw data, absolutely not, but the calibrated data, we're getting there. So I think for PM, we do a pretty good job. For the methane, we can develop, I don't want to totally give away Chulu's message, but, getting things to work well in a training data set, but then actually maybe being able to make it like work on a testing data set has been a challenge for some of the sensors. So the NIST sensors are also pulling from a tower, and then the rest of our sensors are at the ground. So there's also like that level of complexity that we haven't fully addressed yet. So hopefully also the co-location of the garage with Pete's data is going to help us kind of assess some of that uncertainty. But it depends.
Maybe squeeze in like that.
Yeah, thanks. So I'm curious if you compare sort of what you see at the local level with your sensor network to monitoring station data, which is more regional. So how much higher are the concentrations you see like kind of in various places around the city compared to what this monitoring station?
Yeah,
data
for
says?
PM, we don't see typically dramatic differences across the city, which actually considering we have a low cost sensor network, so I think they all agree quite well about it, right? But we don't see huge differences. I think maybe with NO2 and some of the other gas-based pollutants, we will see stronger, so. I was working on that, we're trying to get some of that data into PM being kind of more regional. Maybe it's a shocking here and seeing huge differences. We do see some kind of short-lived plumes from the
Right.
kind of event.
Things tend to
but,
fall pretty quick.
Yeah, as soon as you start averaging up to days, weeks, months, seasons, years.
Right.
Yeah, so.
All right. Next up, Ben. One of the Bens.
Hi, I'm Benjamin Nault. I'm a research scientist in environmental health and engineering, working closely with Pete DiCarlo, Scott Miller, and air quality, and Kirsten as well for greenhouse gases with Scott Miller, air quality for Kirsten, even though we like to try to encompass greenhouse gases with ourselves. Today I'm going to be talking about the stationary site. The location we're at is a temporary site. We're still trying to get a more permanent site, and that's been a fun political discussion that we don't have time for, but I'll get into what we are currently measuring. So for people that haven't been thinking about the air quality, these are the questions that we're generally thinking about. I'm not going to read each one, don't have time for that, but the things that we're working on right now with the ground-based measurements, I'm highlighting in blue, looking at the temporal variability of the air quality that we've been measuring since March, and what are the relative contributions of different emissions within the source, which I'm going to be highlighting. Burger King sometimes is a very fantastic source in the location we're at. The purple are things that we're going to be thinking about a little bit down the road, and Pete's going to be highlighting that with the mom and pop mobile laboratory about the spatial variability. And once we're able to get our more permanent site, which we'll be looking at indoor, outdoor air quality at a row home, we'll be looking at the built environment, how that impacts the air quality coming into where you're spending most of your time. So our current location, I'm showing right here on Google Maps. So the red dot right here is the garage that we have our mobile laboratory parked at, and it's where we've also set up our long-term monitoring site, even though it's a short-term location. And it's fairly close to campus. As I mentioned, we're right here by Burger King, and there's a bunch of other restaurants around the location that are being built up as the community's undergoing development, and we're also close to 83 right here. There's a recycling center right here. So we're also seeing a lot of traffic related to cars going into dropping off recycling. We also can tell when it's garbage day because NOx and CO, other things start going up when garbage trucks are driving by. So it's somewhat representative of the typical urban area, but there are some strong influences that we're still trying to figure out how to filter or think about what that means for general day-to-day air quality. So what's really nice about this site is we have this open access roof. So what I'm showing right here is our gas and aerosol inlet that we've built to sample at the site. And as Pete and Kirsten have mentioned, we are also have the search node co-located here. We also have a Quanta AQ, which is a medium cost sensor co-located right here. So part of what we're looking at is how well do these low and medium cost sensors compared to scientific grade instruments, and what does that mean for community science and how community members can try to use these lower cost sensors to understand their own air quality. And we also have Darren's weather station right here as another comparison and something to help us understand our measurements. So here's what the measurements that we have for our long-term measuring site. We have a scanning mobility particle sizer, which gives us size and volume distributions of particulate matter. We have a measurement of particulate matter black and carbon mass concentration, aerosol mass concentration, composition, and organic aerosol information, specifically primary versus secondary, which I'll briefly get into. We're also measuring ozone, nitric oxide, nitrogen dioxide, and our greenhouse gases of methane, carbon dioxide, and then a vehicle emission tracer of carbon monoxide. We'll be adding some new instruments soon that we're ordering with Morgan State of a new ethalometer to have black carbon and brown carbon, a new trace gas analyzer that will better be measuring ozone, nitric oxide, nitrogen dioxide, and others. And then as we find important temporary intensive measurements where we'll be measuring formaldehyde, speciate volatile organic compounds, and organic volatile oxygenated volatile organic compounds with gas chromatography and proton transfer reaction mass spectrometry. So here's a brief example of what our measurements have looked like. We started around March 31st, and what I'm showing on the top is carbon dioxide, middle is carbon monoxide, and bottom is methane. And what we see is both kind of this urban background as well as these spikes. And these spikes are not instrument noise. They're lasting more than 1 second and are representative of different sources that we're experiencing. And for example, the carbon dioxide and carbon monoxide are due to vehicles driving by or going to that recycling center. And then the methane, there's a lot of methane leaks that are known throughout Baltimore. And we have a backpack that allows us to walk around and measure the methane. And I found a couple methane hotspots within the neighborhood that we're also doing these measurements. So Scott and I are really interested in trying to understand what these methane leaks are and what they look like. I'm also started working with Shulin and trying to validate the methane with the search along with our measurements to try to have better long-term measurements of methane around Baltimore. But some of the big questions are, what are these spiky sources and how do they potentially differ from the background sources that we're seeing? And how does it change over the season? We only have a couple months worth of data, so we still need to see how the seasonality changes for these gases. One thing that you can start thinking about looking at is how does the temporal variability change and compared to time series? So time series, you can see these spikes, which are indicating local sources. But if you average it out into your 24-hour average, you start seeing a temporal variability, an impact of boundary layer height, seasons, and things like that. Another one is nitrogen dioxide that I've started working with Lalitha and Amira, who are both students in our group, and we're seeing high amount of nitrogen dioxide during rush hour traffic, as you would expect, and then boundary layer growth and oxidation, nitrogen dioxide is going away, and then we're starting to get the boundary layer shallowing and more nitrogen dioxide emissions during the afternoon. So starting to understand where this nitrogen dioxide comes from and how does that impact local air quality and chemistry. Real briefly, here's the time series of the particulate matter that we've been measuring with our aerosol chemical speciation mass spectrometer. On the left is organic aerosol in green. On the right is inorganic aerosol, which includes sulfate, nitrate, and ammonium. Yes, if you're using our data, you have to follow these colors, or we're going to find you and discuss with you why you're using the wrong colors, because 30 years, our community's been using these colors. If you use anything else, we get confused in exactly what you're trying to present. But you're seeing spikes of organic aerosol. That organic aerosol is most likely coming from Burger King, but we're still trying to understand that. But what's been really interesting is the amount of nitrate we're seeing, as well as the amount of sulfate. So if we look at that in a fractional composition, what I'm implying here is the mass fraction of these different species. We're seeing organic aerosol is the main mass concentration that we're seeing. But early in the season, when it was cooler and wetter, we're seeing a lot of nitrate, and that's due to the thermodynamics and boundary layer. But as things have been warming up, sulfate is starting to contribute more, and organics are starting to contribute more, and that's due to changes of emission. So it's really trying to understand how the emissions interplay with boundary layer heights and dynamics and temperature and relative humidity, and how these change with season. If we look at estimated organic aerosol contributions, we're seeing almost a 50-50 split with different spikes of primary organic aerosol, which is directly emitted. Trying to understand what these different sources are is important. And this is my final takeaway picture and figure is the diurnal cycle of nitrate that we're seeing its highest in the morning when you have low temperatures, high relative humidity. Organic aerosol staying relatively flat, which means that with boundary layer shallowing, we're still getting different emissions that are competing. That's keeping organic aerosol constant. A large fraction of primary organic aerosol where we're at, and the organic aerosol is relatively highly oxygenated, which means it's somewhat aged in what we're sampling. So with that, I'll take any questions. Thank you.
Great.
Yeah, and popular.
Yeah.
So it looks like the location, it's very close to those recently implemented traffic calming measures.
Yes.
And I'm wondering if it was in time set up in time to catch up with the changes.
No.
But I'm also, are there data sets that are looking at the effect of traffic calming that might just be useful for you all?
I don't know how close.
The search network would be the closest thing since they've been monitoring since 2018. So I'm not sure when the traffic calming started since I just moved here last year.
So it's within the last 11 months.
Okay.
I don't know exactly where it is either. I'm usually public health campus, but yeah.
To me, those traffic calming has always been in that location. So
Okay, yeah.
we had a second.
Yeah, this is totally outside my area of expertise. So everyone complains about the weather, but nobody does anything about it, right? So like, what are the management alternatives for improving the air quality? Like, so it varies over time and over space. What are the choices? Like electric trash car, trash vehicles?
So basically going from fossil fuel buses and trash collectors to electricity, or as a short-term methane, because that reduces the type of air pollution that's coming out of the tailpipes, including small particulate matter, nitrogen dioxide, all these things that lead to poor air quality. So transition from diesel and gasoline to natural gas to electric. We have a very outdated infrastructure for methane. So this is why Baltimore is prone to really high methane leaks, especially in the black butterfly, that as you get into the newer neighborhoods that are in the suburbs that have newer infrastructure, there's less methane leaks. So really focusing on the infrastructure is a big thing as well.
So kind of related to that is so they've been working to solve all those problems for a long time, right? Nitrate deposition is half of what it was 20 years ago. Sulfate deposition is 1% of what it was 20 years ago. And so you have a really interesting question about the interaction between climate and extreme events. And so some things are increasing the potential for extreme events, but there's all this other stuff that's decreasing that. So do you have some thoughts about how you're interested in air quality that interacts with climate, but also air quality that interacts with all the stuff that's like ozone's going down and nitrate and sulfate are gone, and so. It's so you have some way of putting it in a larger context.
Yeah, we are thinking about that. One of the big things, and Chris Hennigan is also interested in these type of things, is the urban heat island effect, because that causes things to be lower relative humidity and warmer over Baltimore compared to the surrounding area. So how does that impact the particulate matter that's being experienced, and how does that change with warming climate? Another big aspect is, since sulfate's been going down, this is changing the chemistry within the aerosol. That's actually making it so there's more nitrate in aerosol. So how's that changing the deposition of ammonium and nitrate into the Chesapeake Bay? Another big important question is, since we do have bay circulation, how does the ammonia from the eastern shores and all the agriculture there come over and potentially impact the air quality of Baltimore and the nitrogen deposition? So we're also looking at these big picture, long-term things.
You have 1 minute, you wanna ask the question? Mike?
Yeah, sure. So, you showed there that a lot of the aerosol was relatively oxygenated. On the previous slide, you had the SOA versus the POA slide. So I'm wondering if that implies that most of the SOA is highly oxygenated, or how much of it is low versus semi-volatility, because this affects the indoor modeling we do, right? And how it repartitions as it comes inside.
That part is, I'm still trying to figure out how quickly and what's the best way to process it for people to have, because we're collecting so much data. At what frequency do I do PMF versus other types of analysis to get that information? But the other aspect is, yes, we have about a 50-50 mixture of POA versus SOA. Some of this POA might be oxygenated since it's coming from oil and deep frying and things like that. So even though it's oxygenated, could be secondary, could be the oils. Yep.
That's all right. Pete's
Thanks.
next. Pete, you gonna do the screen?
I'll be
share?
at coffee.
Yep. Hold on, I'm finding it. All right, you guys see that?
Yeah.
All right. So I'm gonna hit on two quick topics that will draw from the first two talks, and then also I think lead into the final talk. Starting with the mobile, this is Mom and Pop out on its maiden voyage in Baltimore. And I think one of the things we want to be able to do with the mobile lab, which is essentially if you package the fixed site as much as possible and put it in a van about the size of an Amazon delivery van and then drive it around and make measurements while you're driving, that's kind of what we're doing with this. This is technically not covered by BSEC, but it's an add-on that we're excited to have and test out for the other projects that we need this for. But one of the things we can do with that is really link some of the spatial gradients and measurement that Kirsten talked about with the search network with real-time measurements with these kind of more research-grade instruments. So the search network has the benefit of 24/7 coverage, and going back to as far as 2018, we'd be doing episodic coverage, but kind of in real time to cross-check some of those measurements with things like the mobile van and get some of that chemical speciation for particulate matter, for example, that Ben was just talking about from the fixed site. And so that's one of the things we'd like to do with that. Just an example, this is something I did, wow, a long time ago when I was a postdoc, but we did this sort of work in Zurich and in Barcelona and actually in Paris as well. It's terrible to have a postdoc in Europe. And we're able to map out spatial differences in PM and figure out what was causing those. And for the most part, it was actually traffic. And so again, this ties back to that traffic theme. These local contributions, the HOA, this kind of lubricating oil from engines and black carbon were the main drivers across the Zurich area for what were higher concentrations in some areas compared to others. And so we want to be able to do similar things in Baltimore and see if we get results that are different, if there are certain areas and sources in those areas that we can pull out chemically in the particulate matter. But that's the type of thing we should be able to do using the mobile lab and driving around Baltimore. We're also interested in VOCs, and in some cases, PM gradients aren't large. This is work that we did in Philadelphia in 2021, or just south of Philadelphia, actually north of Wilmington, looking at a highly industrialized neighborhood. We saw that the PM concentrations across this area, these dots that you see here on this map, are where we had low cost sensors, medium cost sensors, if I'm being precise. And we saw that the concentrations between the sensors actually didn't vary very much. And this is about a 7-mile tip to tip area that we're looking at. But what did change were hazardous air pollutants, things like formaldehyde, which were coming from some of these industrial sources. And so again, in the mobile lab, this is a concern, I think, at the community level. What is my air quality? What is potentially causing health issues? How do different neighborhoods experience poor air quality? And maybe it's not particulate matter. Maybe particulate matter gradients aren't large, but it could be these hazardous air pollutants, things that we know cause cancer. This is, for example, formaldehyde with higher concentrations right in this neighborhood and lower concentrations in the neighborhood over here. And that's just one chemical. We can look at many, many other chemicals. And so this is another thing that we can do with that mobile lab that we're excited to start doing. You can also do that with methane, which has been done many, many times. I would argue, actually, I would argue one of the things that Ben just mentioned, one of the differences in leakage rates between neighborhoods isn't necessarily newer infrastructure, it's where repairs get done. And so the priority for repairs often is a neighborhood by neighborhood thing, and it's not necessarily equitable. So the decisions to do the repairs when they find a leak is something that also has to be thought about in those contexts. Air quality supersite, this is kind of a pictorial example of all the different measurements that we have planned for that. And then the idea is not only to do it outdoors, and this is what gets into the final talk, but also to do it indoors. And so we've done this previously in a classroom building at Drexel, in Alaska in a home, and in an HVAC at Hopkins campus. And now we're going to try to find a residential space in Baltimore to do the same thing, where we're actually measuring outdoors for some period of time and then swapping to indoors and going back and forth 24/7 to really understand what happens as air pollution comes into the indoor environment with the spatial with the temperature gradients, with the relative humidity gradients, and how that can change things chemically. And so you get data that looks something like this. The high concentrations tend to be outside. As you bring outdoor air pollution inside, you lose it through deposition in cracks, the way it's filtered, if it's an HVAC system that's actively drawing air in. And so you typically find lower concentrations indoors, and you can kind of make it look prettier if you have the solid lines as your outdoor concentrations of the various chemical species, same color theme that Ben just showed. And dotted line for indoors, you can see outdoor air pollution tends to go down indoors. Indoor sources, cooking, smoking, cleaning, other things can actually add to that indoor burden. Right now, we're just focused on the out to in transport. And why this matters is because things like temperature gradients swap seasonally. So in the wintertime, it's cold outside, warm inside, and that temperature gradient can actually volatilize components of the particulate matter. Relative humidity drops as you go indoors, and so you lose a water phase of the particulate matter, and that can change the chemistry and what happens. In the summer, relative humidity can actually be higher or lower, as shown here from some of these previous work. And the temperature indoors is lower in the mid-latitudes. So where we cool our indoor spaces, if we have air conditioning, we'll have lower temperatures. This is an issue, obviously, in housing and what the housing type is that we look at. Will it have AC? Will it not have AC? Do you ventilate using open window, or do you ventilate using mini splits, central air? How you do that is a choice, and it's something that we can try to examine. But ultimately, what happens is when you bring outdoor particulate matter indoors, the size of this pie chart reflects the concentration, and then the chemistry, the composition changes. And so in the wintertime, we often have a lot of nitrate outside. Cold temperatures and wet temperatures increase nitrate composition in aerosol. As that comes indoors to a drier, warmer environment, you lose a lot of that nitrate. And you see this blue wedge actually go away quite a bit in the wintertime. In the summertime, gradient is from hot to cold, and you get some other chemical changes. And in this particular work, we actually noticed some residual cigarette smoke contributing to indoor concentrations, which is a whole other thing we don't have time for. But the temperature gradients change, relative humidity gradients change, and this changes what we're exposed to. So linking that back to health, when we're sitting inside in our home and we're not outside breathing what's outside, what chemically are we breathing and how does it relate to that outdoor air pollution that we have better measurements for and longer data sets for? And so that is something we're interested in doing in the measurement thing, but we can really only do this in one place. And so that's kind of where modeling comes into play. A lot of this work is detailed in work from a previous grad student who worked with both Michael and I at Drexel. And then just one kind of plug, we've talked about chemistry differences, things like that. An important thing to note is things like organic aerosol, and the secondary organic aerosol is peaks in the summertime. You have a lot more atmospheric chemistry going on in the summertime. It links up very nicely with ozone chemistry. It's really the same kind of general chemistry that makes both secondary organic aerosol and ozone. However, in the wintertime, we do still see an ozone peak in the afternoon. It's not as not quite as much, and the background levels are higher for various reasons. But we don't see a correlation of organic aerosol with ozone in the wintertime that we see in the summertime. And so this really indicates that this oxidized organic aerosol is chemically different. It's not formed in the same way that it is in the summertime. And so what does that mean from this outdoor to indoor transport, and how do we interpret that? It's going to be something that I think we have some ability to think about with the measurements we have planned for BSEC. So just kind of an overview. Really, we want to use these measurements to identify spatial gradients and augment the search network that's been going on since 2018, support some of the other themes, greenhouse gases. It's also, once we get up and running, we have the ability to be responsive to events like the Key Bridge, or other community concerns. If there's air quality concerns that happens abruptly, we have the potential to deploy and make measurements quickly. And then the indoor air quality measurements really are going to help support the modeling efforts that Mike will be discussing shortly, and really think about what housing interventions make the most sense, which are cost effective, thinking about how those both maybe improve indoor air quality or degrade indoor air quality, and the decisions we make there. So with that, I am happy to take questions.
Good. Why is it mom and pop?
Because I like acronyms. MOM and POP stands for Mobile Observatory Measuring Particles and Other Pollutants.
Was it the one at Drexel Mom and Pop as well?
No, they called it, like, the students wanted to call it Dougie in reference to Doug Getz. So I went along with it, but now that I officially get to name this one, it's Mom and Pop.
Do we have data on the percentage of homes that have air conditioning or other improvements, changes like for heat, window efficiency? How has that changed over time, and how does that increase or decrease vulnerability to indoor air pollution, and then also just to extreme heat? It seems like
I will defer the question.
most of the houses in Baltimore were not air conditioned, and now they're all air conditioned. Not all.
Yes, and I think looking forward, what that's going to mean too. But I will defer the percentage numbers to Mike Bader, I think, who's trying to get those types of questions included in the survey that he puts out. And so we will have much better data on some of the percentages for that. In terms of exposure, I think one of the really important things, and wildfires obviously are something on my mind and others' minds. If you have air conditioning, the health guidance is to close your windows and doors, turn on the air conditioning, and keep the fan going with a decent filter in your HVAC if you can, to minimize your exposure to outdoor air pollution. If you don't have air conditioning, that's summer, and you get wildfire smoke, and the way that you cool your home is opening your windows and doors, you've just massively changed the exposure for people who do not have access to air conditioning. And I think maybe this is a really important point to make here. The spatial gradients that I think we're going to observe across Baltimore are pale in comparison to the gradients in exposure indoors to outdoor air pollution. If you have a modern home that's tight and you have a good HVAC system, you can potentially reduce your indoor air quality load to about 10% of what outdoors is. If you're using windows and doors to ventilate your home, you're essentially getting outdoor levels of air pollution. And so you have the potential from anywhere from 10% of outdoor air pollution exposure to outdoor air pollution exposure in the indoor environment, depending on your housing stock. And I think that's a really important thing to think about when we're talking about, 1 or 2 micrograms per meter cube difference across Baltimore versus factors of 2 to 10 in terms of exposure indoors to outdoor air pollution.
Pardon?
All right, Michael's up next, but I forgot to share the screen.
So that was like the perfect segue discussion into what I'm gonna be talking about today. So Pete mentioned I do a lot of indoor air quality modeling. We have developed a pretty sophisticated indoor air quality model at Drexel called Images, the indoor model of aerosols, emissions, their aerosols, gases, emissions, and surfaces. I will eventually use that model to do detailed measurement at the super site to try to match outdoor to indoor observations, but since that data is not available yet, one of the things I've been working on with a bunch of people here is to start the outdoor to indoor air quality pilot, which I'll talk about today, and really, I think, gets at the heart of the discussion we were just having previously. So, right, so, what we're trying to do as a group is to develop a simulation workflow to explore some certain questions that were just brought up, right? So, how does residential exposure to indoor pollution of outdoor origin vary across the city of Baltimore by space and time? These are our guiding questions. As was just brought up, how do housing differences or HVAC differences or changes in housing behavior impact that exposure? Are these exposures correlated to occupant and building demographics? How can we work with community members to reduce their exposures? And then how will these indoor exposures change according to future scenarios of climate change or outdoor air pollution? So, what we're really doing now is we're starting this general workflow where, according to census tracts in Baltimore, so for each census tract, we're doing a series of developments to try to get data that we can put a bunch of this stuff together and run models. So first thing we're looking at doing is developing annual trajectories of inputs based on an hourly basis. So we're looking at getting things like outdoor pollutant concentrations, meteorological conditions across the city by tract, hour by hour is our goal. Right now, we're just looking at the entire city as a whole, where we eventually intend to make that more heterogeneous over time. We're also developing statistical representations of residences and the residential character by tract. This includes things like the leakiness of homes, the air exchange rates, or the likely air exchange rates, indoor RH and temp, HVAC type, flows, runtime, presence of absence of AC, window opening behavior, things like this. And then we're putting this and this together to then try to predict residential pollutant concentrations across the city. So we're using those outdoor concentrations, meteorological conditions when necessary, building trends, and we're running it through a simplified version of the IAQ model images I talked about just a minute ago. And we're doing that. We can mute that, right? Okay. Okay, all right. So today, what we've done, we've developed and computed, we have hourly PM 2.5 and weather data. Again, I mentioned only on a citywide scale for now. We will refine this moving forward. We have developed the frequency of residential character by tract. So we know on a tract by tract basis how many buildings there are that are residences, and we've correlated them to a particular type of building and characteristic of that building. And then we have now run the model, and we have hourly and daily PM 2.5 concentrations. What we've done, since we're still waiting on the more precise outdoor data or the more spatially resolved outdoor data, I'm going to show you indoor outdoor ratios by season and by tract, and just show you kind of where we're at and where we're hoping to go. So again, starting with this hourly PM 2.5 and weather data, the workflow is currently using the city scale, and we just grabbed some data, right? We have PM 2.5 for part of 2023 from a monitoring station. We have weather data from NOAA. We eventually want to expand and work with others in this group. For instance, looking at the Search AQ network that Kirsten just described, we hope to use some of that data to make everything more spatially heterogeneous. We hope to work with Darren to get weather data from stations around Baltimore and others in the room, and then eventually go from one value or one sort of trajectory for the entire city where we have spatially resolved data for all these things. And then eventually also we hope to couple this with the Wharf Chem model so that we can test future scenarios and then run it over the city and see what happens. Again, like I said, we have developed this frequency of residential character. So now we have tract by tract distributions of what residences look like across Baltimore. This includes data that we really care about for our models, things like leakiness, which is represented by the ACH50, heating and fuel type, AC type, size and age, and many other things. The way that we got this is we had to do a little bit of downscaling. So we have, using this resource called ResStock, we have Puma level housing survey data where for each of these 5 Pumas in Baltimore, we have sort of a good distribution, a representative distribution of what housing looks like, okay? And so this is kind of the best we could get. Then what we did is apply downscaling techniques where we matched certain variables between the Puma level and the census tract level, and we were able to downscale that data to the best of our ability. Of course, this could be better, but this is where we're at the tract level, and we have things like frequency distributions of certain elements in each tract for things like air leakage, heating, fuel, etc. Okay. Then, like I said, we're predicting the indoor concentrations using this modified simple box model, which is images where we have outdoor air coming in, bringing in outdoor concentrations. We have some penetration factor across the envelope that we consider. We can have deposition of PM indoors. HVACs, if they have one, right, can filter out particles. And so again, we are certainly counting for the fact that some buildings have air conditioning, some don't. Some have filtration, some don't. All of this is within the RESTOC data, so we're able to accurately represent this on a track by track level. Put all this together, calculate the indoor concentration, and then we have, you know, either infiltration across the envelope when everything's closed. We also have a window opening model. Okay, and so I kind of talked through all this already. I sort of tend to do that sometimes where we're predicting infiltration and natural ventilation. We're predicting HVAC operation with a fractional runtime model we've developed. So whether your HVAC, what fraction it runs per hour depends on the outdoor temperature and your indoor set point, right? So we've developed models or worked with data where we put all that together. And we have a runtime model which says for this hour, your system runs 20% of the time, right? Because that'll feed into the IAQ model. We had to randomly sample things like filter efficiency and recirculation ACH. We could maybe get better at that later. And then also, one of the things images did well is it considered partitioning of particles as they come inside and change due to thermodynamics, right? So as Pete mentioned, as winter air comes inside, it warms up, right? And you're going to get volatilization of particles as they come inside for certain types of composition, right? And so we don't predict that in the full way that images is capable of. What we've done in the past is we've developed a reduced order model capable of looking at that. Okay, so now I want to show some data of what we've done. So this is just one building in one tract, right, where we took the data and we took the outdoor concentrations and we computed what the indoor concentrations would be based on all the characteristics and the weather and other variables for this one house, which I don't remember, but this would have had potentially an air conditioner, right? It would have had a filter. It would have reduced the data, the outdoor concentration coming in somewhat. We did that for all the buildings over all the tracks and have distilled the results. Like I said, we don't really have very strong outdoor concentration data yet. So what I've done is computed the indoor outdoor ratio across all of the tracks on a seasonal basis. All right. And so the indoor outdoor ratio, this is just a factor that says that the indoor concentration is some percentage of the outdoor concentration. And that's, of course, mediated by the building. The building determines, and the occupant behavior determines what that IO ratio is. If you have your windows open, and you don't run your AC, the IO ratio will be high, as Pete says, or if you shut everything up, you run the AC, you have a good filter, your IO ratio would be low. This has direct implications on how much outdoor pollution you're exposed to inside your residence. Okay, so this is some data. So we did this for every tract. I'm just demonstrating how the model will be working now and even more so in the future. We chose 4 tracks to put onto this plot. 704, which had the lowest tail, and this is all for the spring data that I'm making these. So first off, what this is this is 4 tracks of the indoor outdoor ratios, right? And it's by season, winter, spring, and summer, where these are box plots, where the line is the median. This is the 25th percentile, the 75th percentile, and the 5th and the 95th percentile. So this effectively shows the spread of the IO ratios we expect to get in this one tract by season. Okay, and one thing you can see is that, we've got 4 different tracks here, and some of them represent low IO ratios, which is good. Some of them represent high IO ratios, which is less good for exposure, right? And some of them have, low and high medians, right? And so this pretty effectively shows the spread of what we would expect across tracks in Baltimore based on this spring data. And you can see that a bunch of other tracks are likely to be in here. One thing I want to point out, right, is, it's 4 of these tracks we've chosen here. I don't really know which neighborhoods those are, but eventually we want to work with more people, right, and be able to understand neighborhood level exposures better, right? But the point is that the tool is now working, and we hope to keep working on this and make it more and more refined over time. Now, as was mentioned, housing drives this variation, right? So occupant demographic, accessibility to air conditioning, age of home, all of these things will influence what the indoor outdoor ratios are. And so just to show you real quick, we've kind of run this over all Baltimore, and we've broken down these same sort of box plots by different types of housing characteristics. And the first thing you can see is if we look at IO ratios across Baltimore for winter, spring, summer, according to whether it's multifamily or single family, that doesn't really make much of a difference, right? They're practically the same, okay? If we look at the same thing for age of home, we do see a difference, right? Where age of home really makes a difference on the indoor exposure to outdoor pollution, right? Where the older homes are leakier and you get higher IO ratios, right? And this is a known fact, right? Newer homes tend to be tighter. They tend to have less infiltration rates, right? And so we get lower IO ratios. We also looked at presence absence of filtration, right? This is all in the rest stock data. You can see filtration had a huge impact on weather on the IO ratio. Okay, and so if they had a filter in both their heating and their AC, meaning it was a forced air heater and a forced air conditioner, the IO ratios were pulled greatly down. If they did not have any filters, meaning they had maybe like window units and radiant heating or something like that, the IO ratios went up because the filter wasn't active. And then finally, for my last point, whether the home has AC or not is something we're very interested in, right? There's a lot of equity around whether homes are air conditioned or not. Our window opening model takes into account whether the home has AC or not. So if somebody doesn't have AC, even as it gets hotter and hotter out, they're going to continue opening their windows, where someone with an AC would stop opening their windows at a certain point outside, right? And so we're able to look at those things, and you can see that again, no AC tends to drive things up, less AC, or having AC tends to drive things down, which is better. The point I'll try to make just to end is, like, if you just were to look at the central tendencies of this, it wouldn't be maybe super interesting. A lot of the interaction seems to happen at these lower and higher tails, right? But now what we have is we have a tool where we can start to look at this. So our future stages, we want to include heterogeneous data. We want to associate what we see with energy use. We want to associate it with demographics. We want to run different scenarios for climate change or pollution, because one of the things about this is if we represent the building stock or the housing stock across Baltimore, we could say something like, what if we weatherized this tract? What if we incentivized air conditioning purchase? Okay. And then finally, we want to look at improved visualization methods with things like GIS, which is something my group doesn't do, but we want to start to be able to display all this data. So that's it for me. Sorry if I went long. Thanks, everybody. Everybody that's been involved in this to some degree is listed up here, so appreciate it.
If you want to ask a question and hang around, you're welcome to, but it's coffee break.
Yeah, so you are only looking at.
Currently, yeah.
No indoor.
Not right now, right? We had to start with, I think, the easiest thing, and outdoor and indoor is much cleaner. Indoor emissions are so widely varied. We're gonna try to add that on later, but we didn't start that.
One of the reasons I ask is. Every mention there's gonna be. Look at the outdoor data. Very important. It's nasty, like, so, yeah, so there is. There's one. Tonight, right? Something was talking about cigarettes.
Oh, that was the.
Because they, I had the same questions from out, I think it was so bizarre, I was telling you, I wasn't gonna die.
Is that better?
That was the last part.
It's hard to hear if there are questions because there's a lot of chatter in the room.
So what we did is when we developed that.
This one here? They're all, none at all.
Can do that, and we do want to get to that.
Yeah.
Drive me crazy. So are these gone?
No, so I turned, there was one here that I turned off. I don't know how.
Here you can, this is the best if you use this.
Yeah.
Okay, I'm just gonna start. So we've got us, half an hour. I wanna be able to see what's going on.
Come back.
We've got a half an hour discussion about summer field work research. We're not very organized. We've got several short presentations. One slide, I'm gonna break that just to And then hopefully we'll have time to have some discussion to see whether there's things missing or whether there's coordination or just to let people know what's been planned in case you want to be involved. So I'm gonna start with talking about the surface weather station measurements that we've been doing. And so this summer, we're planning to keep expanding the station network, and the hope is to put a few more weather stations in Broadway East, because Broadway East is where one of the flex towers is, so we're trying to get better measurements for that area, and the modeling groups are doing that as well. At the same time, we're also going to be deploying this network of sensors that you might have seen as you walked into the entrance of the building. So we've put these sensors that just measure temperature and relative humidity, and we've scattered them just around. There's 8 of them, a couple across the road, and some in the trees, and one by the entrance. That's a couple of images. And so this is the pop quiz. So they're up yesterday. So how much, what's the range of the temperature, the maximum daily temperature do you expect by these sensors that were put within 30 meters of each other?
5 degrees.
Yeah, okay. And if you give me an answer, you've got to tell me what your unit is.
5 Celsius.
5 I guess 5
Okay,
Not 0.1.
not 0.1. So the answer is around 3 Celsius.
Oh, yeah.
So,
The gases.
so the black line here, if you can see, there's a weather station that's on the roof. And then the spread that's here, and the kind of the ones that are the hottest are across the road that get into the sun. And then the coolest ones are in the shade of the trees. Overnight, the spread's much less, the exception. So we're going to do this. And the reason we're going to do this is because unfortunately this 3 Celsius is kind of the variation that we see within the city. And so we're out of the weather station network. We already know that there's variations, but currently we don't know whether 2 weather stations that are different by 3 Celsius is because their 2 neighborhoods are different, or because one of them is stuck in a different location than the other. And in the urban environment, we can't put them all out in the open space. So anyhow, so that will be the second thing we're doing. And there's also preliminary talk of maybe doing some mobile sensors using handheld or a bike. So that's going to be a plan. And so there's several undergraduates who are going to be helping with this, and potentially with some of the community members in Broadway East will help with some of the sensors. Okay, that was my thing. Who's next? Who do we have? I'm just going to go through order. This is Ben. Yep. We'll go through this quickly, and then we'll have, rather than having questions after each one, I think it might be better we can get through this quickly and then have a. I hit the wrong one. Sorry. Oops. Yeah, it's going to hit that.
All right, so as Pete mentioned, our mobile lab is getting close, so we're tentatively looking at some intensive survey drives through Baltimore at the end of June and possibly middle of July. So these will cover methane, formaldehyde, nitrogen dioxide, some particulate matter and things like this. So start getting kind of idea what the spatial gradients of these different pollutants look like across Baltimore. We still have some instruments to finish installing at our temporary fixed site. A big thing is starting to really think about calibration procedures for the fixed site and creating data processing analysis procedure for these. And then working with the greenhouse group to try to understand the methane sources that we're seeing both at the fixed site and throughout Baltimore. And another thing in general is if you know any undergraduate or graduate students that have some interest in doing helping with data analysis, because right now it's mainly me working on all the instruments that I showed. Talk to me during today so that we can see if there's projects that they can start working on.
Okay. Peter?
So a lot of what I do is continuation of the long-term data collection that we had in the Baltimore ecosystem study. So down at the bottom, we have this, we just continue this weekly sampling analysis of watersheds. And monthly sampling of greenhouse gas fluxes in lawns and forests and riparian areas. And also some riparian hydrology that we do. And again, the weekly sampling of the watersheds has been a platform for greatly improving the instrumentation. I think Claire's going to talk about that later as part of the water quality. So we have this continued long-term data that's going on. We have a CUNY graduate student, Brittany Washington, who was here yesterday, but she's coming and she's doing a whole bunch of studies on connectivity. And she's going to be collaborating with John Duncan on that, and then hopefully some synoptic sampling of baseflow groundwater to again get a connectivity between the land and the water and how that affects greenhouse gases and water quality and a little bit on climate. And yes, and then we have some teachers coming down. We have a research experience for teachers grant at the Carey Institute, and we have a group of teachers that are coming down to do functional capacity of urban soils. And this reminds me, so one of the, I guess it's not rocket science, but we have meetings every 2 weeks. And so like our soil and veg group and water quality group have been doing great at collaborating. So these teachers are going to benefit very handsomely from the work that Megan and Samantha and Kathy and Ian are doing. And so there's been very nice coordination of our summer research plans. I made this slide because Darren asked me, but I think we've been doing pretty well with this. So we're going to have teachers, we're going to have the long-term sampling, and then a new grant. Thanks.
You did? Leah?
Okay, so this slice is really focused on the UMBC part of water and water quality, because I didn't, Peter was focusing on CUNY and Carey, same areas, we're doing different things. Okay, so we have deployed sensors in some of this, in the same stations where Peter's been collecting water quality data for 26 years. And so last summer we put out YSIs, and this year we're planning to put out SCANs to include, which will give us nitrate and dissolved organic carbon. So at the red dots there. And then we've been pretty successful with doing synoptic water quality sampling in dead run. So we're going to expand that to the Gwynns Falls, where you sample under dry conditions. And basically it's a window into what's going on in the groundwater if it hasn't rained for like 10 days or so. So we're thinking about doing that this summer. So those are the two main activities. We have our stations in place with all the electronics. We're going to add these sensors once we add to the data logger program. Yeah.
Okay, all right. Kathy?
Okay, so these 3 degrees differences are interesting because all of the sensors are in a heat shield, so I don't know why. So they are,
Because the air temperature is different.
so how come the air temperature is not mixing? But anyway, whatever, air is not mixing. So what we plan is.
Stand across the road in the sun and I'll stand under the tree.
Okay, so it's not the shade then, is it? It is the shade. So okay, whatever. So what we're gonna do is, one of our job is doing the soil characterization. So we already took all the samples that needed for that in Howard Park, and we had a few more in Broadway East. So we're gonna do a lot of the lab work actually related to that. Megan's gonna talk about this. Some of this work is actually part of our larger scale soil characterization, which also involves just looking at what we have already and where the gaps are. I would like to, since there is a 3-degree difference between the shade and the sun, how that might affect actually soil temperature and, more important, soil moisture on the surface. So with the short-term measurements where you are putting out your weather stations or your air temperature sensor thingies, we would like to have coordinated soil temperature and soil moisture measurements. we're gonna continue on, we have one student who is interested in community engagement, and so working with Tempolex and so on that I listed. So we're gonna go out and collect soil samples just particularly for soil quality measurements, not just metals. And then this is something that I didn't mention. We also do some work at this veterans organization, say Urban Farms. The sixth branch where we're comparing their improved and unimproved patches. They manage those big vacant lots, which are essentially a big a lot. So it's not just one lot, but an entire area. We're gonna do some comparative soil quality measurements there. So Megan's here.
Okay, this is the slide I didn't have time to talk about yesterday. So we have two big projects. This one's being led by Sam, who is a graduate student. Who's right here. Wonderful. Hey, Sam. So we are going to look at 14 tree species. These tree species are split into many different functional groups. Like we have broadleaf trees, big leaves that are both deciduous and evergreen. We have pine needle trees that are both deciduous and evergreen. We also have scale leaves. So these are the 14 species. We have 5 replicate and 3 land use types. And our 3 land use types are street trees. Street trees we expect to have really very low biotic competition because they're planted pretty far spaced from one another. They're not really competing for light and they're not really competing for below ground resources. But we expect it to be really a high stress environment, right? It's not a great place to be a tree. We're going to do this in residential and park trees where here we expect there to be low biotic competition. Generally trees are spaced far apart from one another, and also people water, they add nutrients. It should be like a really plush, happy environment for these trees. And then we're gonna do urban forest trees where we think this is gonna be mid-environmental stress because they are actually competing for water and other resources, and there should be really strong high light competition. So we have these 3 really different contrasting urban environments. We're gonna measure all these trees. We're measuring a suite of tree traits such as photosynthetic capacity. And I spoke about these curves yesterday. We're measuring how big are they? And we're measuring a bunch of leaf traits. All of these are things that are really wanted in the ELM model that Dan will be running. And we're going to do a co-located mini soil measurements that are being run by Kathy's lab and by Peter and by Gift here. And so we're going to be looking at soil texture, soil moisture, soil nutrients, microbial activity, and trace gases. So that's experiment 1. That's flavor 1. Flavor 2, we're doing some model conductance. So for this, we're going to be co-locating work with Kathy, who's going to have measuring soil moisture at various depths continuously through time. So like the soil moisture at the other place, we're going to put down a machine, press a button, it's like beep boop, this is your soil moisture, right? Like it's kind of not that accurate, but it's good enough. This is going to be really accurate soil moisture. That's going to be also co-located with some of Darren's weather stations. And we're going to have an undergraduate go out 2 to 3 times a week and measure stomatal conductance. How open are these stomates? And so that's what they're doing.
Okay, great. I think that's all that I had. Is there anyone else that has some summer field research plans that they want to mention?
Well, just one thing that we should mention, since we're talking about soils, is, and maybe Nancy can give us an update on this, but we got the USDA is gonna map soils in Baltimore and make a new map, which is a big advance.
Ian here?
Where's Ian?
He's leading it, but yeah.
Are they going to?
NRCS is coming
Monday.
Monday, and we're doing a tour, which Ian is coordinating and picking sites and looking at soils and.
So they're not gonna, so it is up in the air. They're gonna come to visit site, they start to dig and they start to think about whether they want the city-wise reconsidering everything that's been called urban soil, or they want a more intensive one in looking at local or more smaller scale variability. They're gonna do something. So they're gonna refine the urban soils. May not be a back.
Can't let him back out now.
Huh?
We can't let him back out.
Yeah,
now.
okay,
You know, that
sure.
we've come far enough, hopefully.
No, to me, it's a great accomplishment.
Yeah.
And I know that you bothered them, and Morgan
Yeah.
bothered them, Kathy, you know, but because if we want to scale, right, so you have all this information we're collecting on soils, we want to scale to the whole city to match the other things this map should help with.
Yeah. And I think Ian's gonna take them to Duncan Street
Yeah.
Garden, which, so that's at least, so there'll be some kind of coordination. Yep,
Will they map and classify fill?
Yes, I think that's, so essentially but so far was considered to be urban field.
Yeah.
Those are the, so they're gonna wanna go to some vacant lots and, you know, definitely anthropogenic, recreated soil.
Right, I think I have a related note, we don't just measure, right, we also want to simulate and use these measurements. So I know at least one person, I'm pretty sure that Jason Warren is planning to work on this large A simulation work with the summer 2024 focus. Be good to think about whether the folks are gonna be running numerical model experiments that we utilize all this kind of data.
Can I follow up on that a
Yeah.
little bit? So I think, I just heard like the ELM was mentioned. And also we have this, wolf running by a lot of our folks in atmospheric dynamic thing. And for example, wolf has three major tables. One is land use, the other is vegetation, the other is soil. And basically they are like lookup tables. And with all kinds of parameters inside. It would be extremely helpful if we can actually get some of the parameter estimates from the measurements. And we can compare to the, like, the lookup table and for the specific type, how far they are from each other.
Okay, sure.
Can I add
we're
one
working on
note?
that. Yeah.
Can I add one note to that? Not only the parameter values themselves, but the spatial distribution and how it's represented in the model's framework in comparison to what you guys see on the ground, right? Because I do think it's a little silly right now what's going on under the hood and what's in there. It's producing results, but how representative is it? That's a whole different question. And if we can ingest better static data in the form of soil characteristics, et cetera, I bet it's going to help model these urban heterogeneities to a better extent. So yeah, not only the parameters, but what it looks like. And I can work on putting something together for that, right? What does it look like right now in WRF's modeling framework? What does the soil in Baltimore look like? Produce some sort of, I don't know, some figure. And I can send that over when I get a little bit of time. Yeah.
Okay, thanks, Jason. Derek?
Yes, I just want to ask, I just saw that there is some, let's say some data activities related for the bulk density of the soil or the bulk density of the moisture content. So I just want to ask if the community want to get engaged in those activities, they will be only limited to collect data or to provide some measurements, a lab work and measurements related, let's say, for example, for the moisture content, which equates, let's say, novel to cultivate it, or it's only for active fieldwork activity.
So I think we're open for whatever the community, if the community's interested in helping with data analysis, helping with collection, that would be great. And so I think at the start, we're thinking of if the community can help with some of the data collection, that would be the first step. But then I think we've got, if there's people who want to do involved with data analysis, then that would be great.
The community can be involved in sample collection as well, that we can process in the lab or doing some on-site measurements. But I mean, we need to talk about it, what's useful or mutually beneficial. That's what that.
And I think for the big tree sampling campaign, we're taking a big bite here, right? And so I honestly think like when they're gonna try and go to 6 locations each morning, and then there's like hours of field work back here, like I don't think it's a good example for the community to come and hang out and do the work with us. People are gonna be stressed in the field, and we gotta get the plant samples and we gotta get out as fast as possible. But if there are interest in the community things, we could create separate events where we're not trying to collect this core data and teach people what we're doing and showing them how they can collect this, but it doesn't make sense to have community members come and show up. I don't think it'll be a pleasant experience for anybody.
Because you need to really concentrate, I mean, they can not see that, when we're doing field data collection, it's an enormous amount of concentration, it's the same thing when we're doing water quality stuff. It just can be a real distraction and people want to watch. You don't have time to really instruct, you don't even go and collect.
Just a quick note, I had asked about the process and we had talked about it. Scientific committee has ideas, we go kind of do the paintings and to Aaliyah, say we got this idea. From the other direction of the community has ideas, it should kind of come the other way. We should get it to Aaliyah and then bring it up to the painting and say, okay, what makes sense? I think those kind of requests are great.
So, I mean, Mike and Cora are here, they do our weekly water sampling collection, and they've got pretty good at hosting small groups, especially when there's heavy things to be carried. So we welcome some, and I mean, you can speak up, but I think if people look on it, and it's actually our weekly tours, it's a great experience of the urban to rural gradient in Baltimore, and so if we had some community members who wanted to come, and were willing to carry. I think, am I right about that?
Yeah. You just have to figure in the van or the, yeah, right, because they can take two passengers.
Yeah, or if another car follows.
Yeah.
But I think we've been doing it for 25 years. I think it's a little bit easier than, I think what Megan and Claire say is very, very.
That's different, yeah.
But they're not, do they look stressed?
So you guys have to.
We might be able to do something.
One other meeting measure that I think I know is gonna be happening that we'll hear about tomorrow. I believe that a NASA group is going to fly a flux aircraft.
That's part of the driving that we're doing, that I'm not sure if Glenn's gonna be here tomorrow to present, but I can
Glenn
discuss
is
real
going to be
quick.
here tomorrow to present, and I believe he's flying a flux aircraft over the city.
So there'll be 3 or 4 flights over Baltimore to look at CO2, methane, and nitrogen dioxide fluxes. And it will be 3 times throughout the day to get morning, lunchtime, afternoon to really see what the fluxes look like. So that will be the week of the 17th through the 22nd. Then the next week, there's going to be a undergraduate internship program with NASA where there'll be airplanes flying over Baltimore for 1 or 2 days to look at air quality for the students to process. And the mobile laboratory that Pete and I are running will be driving underneath them to get some ground-based validation of the measurements to go with the aircraft measurements. So the last 2 weeks of June, the sky's gonna be busy with NASA flights.
So that, I mean, I'm gonna be away, but we've gotta find a way to communicate this with the community. I mean, driving a van around and flying a plane over Baltimore is, doesn't a very good history of surveillance that's gone on over the city. And so that's what, I'm sure if you mention this to our community partners, that's gonna be their concern. So we need, if it's, you're talking within a month?
2 weeks.
Yeah, well, we should note that this was NASA planning. We were not engaged in planning of this.
How high does a plane fly?
Low flying aircraft.
What was that?
Just wondering about altitude.
1,000 feet.
1,000 feet.
It's really hard to get permission to do that. I mean, you know, we're all.
It's NASA.
It's the air traffic restrictions are upside down cake around the airport. So if you're low, it's actually easier. Than if you're higher.
Actually fun.
So it's a B200, P3. Normally, they also have other types. I've been doing NASA airborne stuff. Ken's been doing it longer, but we can describe all the airplanes.
So we should, tomorrow that should come up, we should find out, get all this information and make sure. I think that we should make sure that BC tries to communicate this, even if it's a NASA activity.
Yeah, we should try. So here tomorrow.
Yeah. Okay. I think, is there anything else or? Nope, okay. Who's next, team?
Who's next? It's time to move on then to water.
Giving water 5 minutes.
Yeah, water. You have
5 extra minutes.
Yeah. No, this is not really group, so next we're probably is probably. No, they can't.
So let's see, what's up first? Let's see, Claire, where did this, yours and my talk get downloaded to? The download folder.
That
So
download folder.
let's go to downloads and overview, the third one from the top.
There you go. I am screen sharing, good.
Okay, great.
All right,
So
you're on.
we have five, count them, five talks. Answering a set of different questions that the water and water quality group and with a strong overlap to the urban flood cross-cut theme have looked at. Where does water, where does rain go when it falls? So what sort of surface or subsurface flow paths does it actually follow? Natural and built drainage systems, how does that impact runoff, stormflow, nutrient sediment, and so forth? How do we measure it? How do we analyze it? How do we model it? Green, blue, gray infrastructure. How do we design this? How does it actually behave to mitigate some of the flooding and water quality issues that we're looking at? And finally, what are the main factors for spatial and temporal variability of what's coming down the drain into Baltimore Harbor? So Ray will pick up on this. So these two are largely looking at the watersheds writ large, in other words, from city to county accumulated. And then Ray will pick up, so what happens when we get down into this region over here? Let's see, so we have five talks. The first one Claire is going to give. This is based on a set of people that are working on this. Claire, James, Shirley, Andy, Mary, John, Peter, and so forth, arrayed around these different watersheds. Some of these are long-term data that we have, but these are being augmented with BSEC funding for more advanced sensors, both at the level of the individual parcel or at the abandoned field, and then in other areas. Next talk, so this is all the new instrumentation that's going in. Next talk, Julia and James. Julia will be presenting on some of the certain largely surface water. So we talk about flow paths, surface to subsurface. These emphasize the surface flow paths, both overland flow and pipe flow in selected areas for major events, and then coming up with design storms themselves. Then we could start building in the type of mitigation strategies for those. We'll follow up with Roy giving a talk that starts to integrate surface and subsurface flow. We've had a set of discussions with DPW, Department of Public Works, about this differentiation between surface water dominated events, which are often warm season pluvial or intense rainfall events, and the type of flooding we saw this past fall to winter. Andy looked through and said this was the wettest 3-month period, I think, between October through December in a period of time.
It's not entirely clear because Kim had one study. I think it was probably about at least 8 to 10 years.
It was a very wet period of time. Maybe not the wettest period of time, but we saw all these events in December and January that were characterized not just by river flooding, but a lot of basement flooding. A lot of people were talking about subsurface seepage into their basements. So this is really an eco-hydrological model and will characterize both water, carbon, and nutrients. There's a set of other models that we're running right now that I don't think we're presenting on today that do the surface subsurface characterization. Ava, working with Antonia, will talk about multi-objective optimization for flooding and other potential parameters using some advanced methods to look at the different types of goals that we have. So this gets into the XLRM area where we state, here's the set of goals, here's the set of levers. I think they're using a SWIM model at this point. We'll hear about it at this point to look at deep development of deep uncertainty regarding these for a specific watershed here. And then finally, Ray is going to pick up at the end with what happens to all the water and nutrients and other pollutants as they go down the drain into the Baltimore Harbor. So there's a set of people working on this besides Ray. Julia's working on this. We had a discussion with Harry Wang at BIMS the other day, who's running a very high resolution model for the Baltimore Harbor. So this is actually the set of talks we're seeing will go over this full region from watershed, county, city, to the down to the estuary itself. So the first talk then, before we go on, questions. I think we're
Posters too, right?
yes, thank you for the posters, particularly for cross-country, so all cross-country, cross-cutting. Other people do cross-country. We'll call a set of posters that you'll see. I'll emphasize also Kelly Lombardo's paper on NextRed precipitation over a set of areas, and I'll ask others with posters related to this to just call attention to theirs as well. So in that case, other questions on this? Things that we may be missing on this or other areas of discussion? Not, we'll save some time now and we'll have more time for a discussion later. Put this down, and up first is, I think, Claire.
Shirley, Claire, etc.
Claire. Shirley is not here.
Is joining remotely. And I put her slides in. Okay, so let me see if I can stand on the side. Okay, so I'll stand over here. But if there's no remote, you just fix. Okay, so I'm going to give an overview of what we know about so far that we're going to install or have installed with instrumentation on both water quantity and water quality. So this first group here are UMBC and BES folks, and then James Hunter is from Morgan State and Shirley Clark is from Penn State Harrisburg. Okay, so we want to go down. We're going to hear from James about soil moisture sensors. We're going to hear from Shirley about her stormwater super sites. And then I'm going to talk about water quality sensors that have been deployed or they're going to be deployed, and then some applications. So James, you in here? You want to just talk quickly about your slide here?
Yeah, real quick. So we are deploying Sensor Terra soil moisture sensors. We have a pilot of this happening at Morgan State University. But the reason why we're looking at this was it was coming off of another pilot that we had focusing on green infrastructure practices. So how we operate and maintain these practices within an urban landscape. So we're mostly looking at bioswales, bioretention systems. But this is something that we're also going to now expand from our campus into the Old Goucher and Broadway East neighborhoods. Currently, our gateway placed at Morgan State University is allowing us to pick up sensors that we deploy within this green area. We're going to be deploying perhaps another gateway within the either Old Goucher or Broadway East. We're probably going to be deploying that gateway at the Lake Clifton site. So this is an area that Morgan State had just recently acquired. So this will allow us to now expand this map to deploy these soil moisture sensors more in this area right now. Gift, who's here, will be deploying about 24 or 25 of these sensors on Morgan State's campus. We're piloting about 5 of these, but this is something that we can also maybe share in with the veg and soils folks as well, because these sensors allow us to pick up this data remotely. And again, our focus will be on, particularly in Old Goucher, looking at the green infrastructure that they put in over the last couple of years. Some of us went on that walking tour yesterday, so we'll be able to not only look at the dynamics of the soil, and I'm about to jump off, but also look at some of these potential green infrastructure applications that are currently placed within different areas of the city. Yeah.
Okay, so Shirley, are you online?
I am online. Can you hear me?
Yes, I can. And why has my screen disappeared here?
Touch the screen.
Oh. Okay. Oh, all right. Well, that's interesting because I don't have the, it doesn't matter. You can see it. All right. So let me go back up here. All right. Okay. So this is Shirley Clark from Penn State. who is going to be instrumenting stormwater super sites. So Shirley, your first slide is your list of instrumentation, and it's not, yeah, there we go. Okay, go ahead.
Yep, sure. So what we're really trying to do is, and we've heard several people talk about it, is understand the shallow subsurface water movement, particularly as was just said earlier, as we're seeing more people with basement problems and all that. We think there's short circuiting going on due to the way land was developed through compaction. So to test this out and then to be able to plug this into some of the models that we're using, as James and I've been talking about using SWIM, we're going to be bringing down basically double ring infiltrometers, a standard way to do it, to do measurements. We've got several different types we're going to be using that we have. We're going to be also trying to measure gutter flow or inlet box flow, so we understand what runs off the site. So you can think about it as a water balance on a small like land development backyard or an open park space or whatever. That's what we're really trying to do, is understand that water balance in a small set. A part of that also will be soil moisture sensors, not a different brand than the one James just talked about. So he and I will be sharing data with that. And also, again, the cone penetrometer, ground penetrating radar, my colleague got that. And so while that wasn't part of the original plan, since we now have ground penetrating radar, we're going to be bringing that in to better understand where subsurface infrastructure like utility trenches, your cable line, your water line, your sewer line would be on the test sites. So that's what we're looking at. And the cone penetrometer, because some of the models will address the fact that when we do land development, the porosity of soil changes, but we're really interested also in understanding is there a restrictive layer to flow? Because the models right now that we typically use in urban hydrology assume that if it is pervious on the surface, you can infiltrate water all the way down to the groundwater, and it effectively in the model, on a surface hydrology model in urban areas, becomes a water loss from a water balance perspective. So that's what we're really trying to do with that piece of it. So again, with that, what you're going to see again with these ideas is that we've been doing this up here. We're going to get soil moisture over time. We'll also have temperature and electrical conductivity. You can see the sensor installation on the picture. And what we're trying to do on a site is we're going to be looking above and below a compaction layer. And then we'll be looking at that potential restriction of flow. What we've been seeing is the fact that you can definitely tell when the water doesn't penetrate below the compaction layer. And what we've actually seen in some of the sites here, we anticipate seeing in Baltimore, is going to be that if we see the watershed, the water flow hydrograph in one area that lingers longer than the others, we are obviously getting, or which means a higher soil moisture content, we're going to be getting flow directions, and we'll understand lateral subsurface flow direction. Again, in a very shallow depth, not getting to groundwater. We're talking potentially 0 to 6 inches down below the ground surface. And so we're looking at this preferential flow paths. So again, that's what we're trying to do. And then the considerations are the sites we're looking at. We haven't isolated down. North Dukeland's the one we've got to isolate down a little bit further because it is a residential and an open park. And so again, I had looked at the sensors that James is talking about using. They've got a rather large above ground box. My data logger is a little bit smaller, but I'm still looking for sites that are secure. We've talked about going into Cherry Hill, into some of the Baltimore city housing apartment complexes. We're working with Old Goucher Broadway East to find that. And then the North Dukeland area, and there's one also up near Morgan State that I forgot to get down to clear to put on the slide. And so we've got a graduate student who started with some of the modeling and setting up in the spring, Yogesh Joshi, and that's where we're heading for. So I think that's my slides, and hopefully in the time frame.
Yeah, and last week in June is your target for installation.
Target is last week in June, yes. Because the equipment's in, we just got to isolate down the location, because North Dukeland, we're going to have to try to work with a resident or look for something that is going to be small enough that I don't have to worry about it wandering off the day after I install it.
Great, thanks, Shirley. All right. So for water quality instrumentation, per the slide I showed just a minute ago, we've been working in the Gwynns Falls watershed, which has this urban to rural gradient of land use. So on this particular map, the gray is fraction impervious surface area. So this is the location of the watershed studies for the Baltimore ecosystem study, which has been in place since 1998, field headquarters hosted by UMBC. So within the study sites, we have 3 nested watershed sites along the main stem of the Gwynns Falls, and we have an ex-urban site, a forested reference site, and 1 highly urbanized site, which is Dead Run. So we've had USGS stream gauges funded since 1998 at these sites through these grants, and they're all beaming right now at 5-minute data of water level and discharge. And this is what the red dots are where Peter's group has done the weekly chemistry sampling since 1998. So we have 26 years of data, which is really amazing. So, you know, nitrate, phosphate, sulfate, chloride, total N, total P. And so what has been done with this data is, among other things, to evaluate loads and yields. So the Chesapeake Bay folks are interested in loads going to the Chesapeake Bay. And this is one way you can analyze them when you have solute concentration and water discharge. You can calculate loads, and yields are just loads calculated by area. So then we deployed some new sensors in 2023, and what we deployed were these YSI EXO2 sondes. They contain 5 sensors: temperature, specific conductance, turbidity, dissolved oxygen, pH. And then what we have planned at these red dots is where we just deployed the sondes. We have SCANs planned for 2024, which will be nitrate, nitrogen, and dissolved organic carbon. So this is Mary McWilliams, who's sitting here today. She is a full-time staff person in the research center at UMBC Curie. And so she and I design and deploy these things together, and then she maintains everything and keeps the sensors calibrated. So we have these sondes, you know, secured to stream beds because they could get knocked out with cinder blocks, and you know, we have to secure them mainly against storms. Vandalism, we haven't had much problem with. Cinder blocks, rebar, PVC housing, hose clamps. We have the whole communication system and the utility box that's powered by solar panels and batteries. We use Campbell Scientific data loggers. We beam the data to UMBC with Sierra wireless modems. And we manage all the data in a console and database base station with Campbell Scientific LoggerNet software. So that's our end-to-end system for sensor deployment. No, I'm not. All right, well, okay. So, okay, well, I can just, I mean, I had worked on a lot of applications so you can see what this is, but we can also look at Mary's poster. So the applications, you might wonder, well, why do you need this beyond the weekly sampling? So we can look at water quality responses at the storm event timescale. So that gets more refined than our weekly sampling. And you can look at it, the consistency in water quality patterns across storms. And we can try to see if this improves quantification of storm contributions to annual loads and yields. And so given that we're having more intense storms, this could be increasingly important with climate change. So this is what the data sets look like, these high frequency data sets. You can see here, I'll stop after this. I had a bunch of more slides, but I can stop. Mary has a poster on this out in the poster room. So this is just 4 of our stations. So what you can see is, you know, discharge. We always scale discharge by watershed area. Discharge is, you know, stream flow. And then you can see how, you know, specific conductance always was typically in non-road salt days, decreases when flow increases, and you can use a binary mixing model to deconvolve that and actually get at the groundwater contributions to storm flow. So specific conductance goes down when storms go up, and turbidity goes up when storms go up. And we use turbidity to correlate to suspended sediment to calculate sediment loads, and sediment loads calculated that are going to the bay are important. You can see over here on this slide, you can see the diurnal variability of temperature, dissolved oxygen, and pH. pH is a little bit hard to see on this scale. You can see it a little bit better down here. And all vary night and day. And so you can see how this changes with just this small snippet of time we have from one of our data snippets last fall. And so that's the kind of quality of the data set you see with these sensors. So I think I will have to stop there because we are out of time. Okay. And you can come to our poster if you want to see more. Okay. Thank you.
I got it.
All right. We're good.
Well, we are actually about 2 minutes behind schedule now. So warning. Can't let Michael win, right? Can't let Michael win. Let me see if I can find Julia's presentation. Darn, come on, stop this weirdness. There, Lisa. Got it. All right, you're up. Sorry, I'm a minute or 2 behind.
Hi everyone, I'm Julia Taye, doctoral student at Morgan State University. and I'm excited to share on our progress research on urban flooding in response to extreme rainfall events in Baltimore. So for our research, we are proposing this watershed, that's Stony Run, Tiffany Run, Eager Park, Fulton Avenue, Frederick Avenue, and Cherry Hill. So we are proposing this watershed because most of these watersheds are found within the buried streams. And also this watershed have historic flooding occurring there. An example of a buried stream is due to urbanization. You see that most of these streams are channeled under a drainage network. So with this extreme rainfall that are recorded currently, there's a surcharge that the drain cannot contain the water that's coming in right now. So it causes flooding within the neighborhoods. So example is the Tiffany Run watershed, and based on the Baltimore Sun newsletter, it says that the Tiffany Run has been recording flooding ranging from flooded streets, basement flooding since the 1911, and this has been a problem within the city. And wanted to find out what exactly is causing the flooding within this specific watershed. So our goal for this research is to develop an accurate flood model, and this will help us understand the type of flooding that is happening there specifically. And this will enhance the preparedness of the community for flood events, and also improve the resilience of the city in terms of the extreme weather event that we are facing currently due to climate change events. So the proposed method that we decided to use is the PCStorm, that's the personal computer stormwater management model. However, we had a delay in getting the drainage network and other data sets from the city. So we decided to use the CityCat model. And the CityCat, that's the city catchment analysis tool. So it's a 1D, 2D hydrodynamics model, which was developed in UK. So we decided to use this model because it does not include the drainage network. However, this model has been used extensively in UK and has been validated against actual storms that happened in the UK. And the validation was quite right. So we decided to apply this model here in the US to see how it's going to give us a results ongoing whilst we wait for the city to give us data to run our PCStorm. So with that CityCat model, the data set that is required is using the topography or the digital terrain model, the building shape file, soil data, and historical rainfall. And this model performs using the greenhouse method, the building hole approach, 2D shallow water equation. And after the model is calibrated and it's run, we decided to, because we don't know how the model performs, we don't really trust it, because it has been already done in the UK. And UK has a different landscape as compared to the US. So we decided to use Twitter reports, Instagram, Facebook newsletter, 311 and 911 to look at how people report their flooding issues on that side. And we use that to validate our model. And at the end of the day, the results will be presented in a flood extent map and in animation to visually see what's happening on ground. So we decided to use the storm event that happened on June 10, 2021. So we decided to use the storm event for Tiffany Run watershed because at that intersection, there was a case reported that at 35th Street, a bus was seen floating at that intersection. So we decided to use this rainfall event that happened on that day. And the total depth that was recorded was 2 inch, almost 2 inch, and the duration was 3 hours. And we also used the parameters that was used by DPW in their InfoWorks model. They had a commercial source model that they had to run. So we wanted to see how our model, that's the CityCat model, compares with the InfoWorks model. And if it performs well, we'll be proposing that model to the city because they don't have to rely on InfoWorks, which is expensive for the city to buy, but maybe rely on CityCat. So that's why we use this event, because they use that in their model. So based on our model running and calibrating with InfoWorks parameter, we realized that this red intersection here had a higher water depth there based on the storm event that happened on June 10, 2021. And we further went ahead to validate the results, looking at what actually happened using the Twitter reports and the Instagram. And you could see the bus floating at that intersection that our model predicted. And most of the streets had the water or flooded streets on that day, June 10, 2011. So we further went ahead to look at the reports that was recorded in the 311 and the 911 call logs, and we realized that on June 10, 2021, at that intersection that our model recorded a high water depth, there was reports on sewer water in basement, flooded streets, and storm inlet choke. So this is a picture showing the model that was run by InfoWorks by DPW, and it correlated well with what our model was giving us. And based on DPW's framework, they realized that this site that had a higher water level, they measured the 5 feet, and our model gave us the highest water depth that the model is proposing based on the storm event that we put in was ranging between 5.121 to 8.21 feet. So which shows that it correlated with what's happening actually on ground. So our next step is to calibrate the model with multiple storm events to see how the model performed, because this is just a single storm event that we calibrated the model with. So we are going to calibrate it with multiple storm events to see how the model performs, and also calibrate the model with the design storm that were used in DPW's InfoWorks model. That's the 2-year, 5-year, and 10-year storm events. And we are going to replicate the model that city cuts for other watersheds listed in the previous slides for Tiffany Run, Fulton Avenue, and other watersheds. And we are going to help increase the awareness on the use of My Coast app. So this is where we come in with the community engagement folks to be able to spread the news on the use of the My Coast app, because we had a limited data to validate our models. So therefore, if people are aware on the use of the My Coast app, when there's a flooding incident at that place, they report on that app and take pictures of where the incident is happening. And it's going to help we as researchers to be able to validate our model at the end of the day. So I'd like to take this opportunity to say thank you to the Newcastle University people for the opportunity to use their model, and to DPW for giving us their InfoWorks parameters to calibrate our model, and to my amazing water and water quality team and Dr. James Santa for their support and guidance through this research. Thank you.
Questions?
Yeah, thank you very much for sharing all this information. I wonder, for the intersection that you showed as an example in your talk, is that almost problematic in storm events?
Yeah, it's always a problematic there. So we decided to find what exactly was causing that problem there, and realized that the elevation is also caused, because when you look at the DEM of that site, it shows that that intersection has a low elevation, and most of the berry streams, it has a historical berry stream, and the drainage network is not able to handle the storm events that's happening. So either we integrate brainstorm water infrastructure at that place to control the amount of runoff that's generated, or we increase the drainage size that's there to be able to contain the amount of rainfall that's happening.
So you're kind of validating based on a different model. You're validating with InfoWorks.
Yeah, so I'm just validating with InfoWorks to see, and validating with Instagram, Twitter, and 311 and 911.
And that's because we don't have a better sense of like how much the flood depth was. So we're going with what the city is doing to estimate it. Could it be that the InfoWorks estimates are wrong?
For now, we cannot really say the InfoWorks estimates are wrong, because based on the flooding that happened at this site, and looking at the high water level there, and based on their measurements, it was measured as 5 feet. So it's not like the InfoWorks is wrong.
So so they validated for that location, and then you're using the InfoWorks outputs to validate for other locations too.
I'm not using InfoWorks, was just run for Tiffany Run, Maiden Choice, and other stuff, but it's not really within our watersheds that we are looking at. Tiffany Run is just to see how our model performs. So that's why we didn't use InfoWorks. It's just to look at the depth. But we didn't use, and we use their parameters to calibrate the model, but not to like validate. It's just to see the figures that they are getting, what we are getting. Yeah.
Very good. Thank you.
All right. Thank you.
Greetings.
Get your, it should be there.
It probably is in a different folder, because we are in the
We downloaded it to the download folder.
folder. Well, we're in the downloads folder now.
This last name should be.
Yes, probably like that.
No, it's not there. It's but I uploaded it to the. Yeah, so if it was there.
You upload it.
To our like. June 5 AM. Yeah. Folder.
So where can I find the ones you already downloaded?
Yeah. I think what's under here.
Presentation, there we go. That's what I was.
Double click on it.
Yep. June 4th, what is it? What is it today? It's the morning of the 5th.
That's not there either.
Not there either. That's weird.
Hang on,
You have the.
We do have the Google Drive. Okay, where can I, where? Yeah, go ahead and you drive.
Sorry, but sorry. Need to get rid of all these.
Enough of that.
Okay. Probably like, this is covering up, I can't. Is it there?
No, no, okay, it's probably. I uploaded like eight-ish.
No. Go on. The drive was there, I didn't know.
We just downloaded all these different documents.
Pardon?
I thought we just downloaded these to the downloads folder. It's not in the downloads folder. No. Have that
It's in the
open as a
upload
scan.
folder.
We're trying to get on these Google Drive.
I'm gonna stop sharing.
Where it should be.
I can't. That was covering that. There it is.
There we go.
So logging up when you download it, you can upload it. Using alternate, automatic, there we go. Yeah. If you're
There.
directly from the. Found it. We're downloaded plus. Which is a two, which is top 3. Then I would have to use the card for software.
I see. Okay.
So either one, we can get an ASCII version. Cool. Awesome. Thank you. All right.
Okay, just reshare this.
Oh, there we go. Download it.
I can share it. Yeah, take it easy. I got it. I got that. That, no, we don't want to do that. We don't want that screen. First, get that out of here. Yeah, there you go. All right, sorry for that delay.
Okay, hi everyone, I'm Roy. So today I'm going to talk about understanding urban ecohydrology in high spatial resolution using RISES. This is more about the overview of RISES and its applications. So just some quick overview about the urban stream syndrome. Like after the urbanization, we have a more impervious areas in the watershed that gonna let the storm events become runoff, and this runoff will be routed through the pipe system and being released into stream in a very short period of time. And in terms of the hydrograph, we're gonna have a higher peak discharge during the storm days after the urbanization. And after that, because we are not infiltrating a lot of water into the soil, we have a less base flow supplement after the storm events. And this is just a big threat of the high risk of urban flooding, which gonna threaten the people living in the floodplain and the riparian areas. And at the same time, human activities introduce a lot of nutrients into the watershed, from legacy pollutants like agricultural activities before the development, and also wastewater treatment, plant effluents, sanitary sewer leakage, and septic effluents. And these will going to affect the aquatic ecosystem health in the receding water bodies, for example, in the Chesapeake Bay, where the oxygen level gonna drop due to the eutrophication. And to reverse the increasing of flood risks and the worsened water quality, we are implementing ecosystem restorations. For example, the terrestrial restoration, including green infrastructures like rain gardens, bioswales along the road. And we also reforested our urban watersheds a lot. Detention ponds is another type of terrestrial restoration we implemented in the watershed. All these kind of stuff trying to hold water and the nutrients in the watershed and prevent them from being directly released into streams. And we also do the aquatic restoration, specifically just the stream restoration to rebuild the connectivity between the river and the riparian areas to rebuild the ecological processes at the riparian zone. So to understand all these kind of dynamics, we need a model to comprehensively simulate water, biogeochemical, ecological, vegetation, soil, all these kind of interactions within the urban watersheds. And here we are using the RISIS model, and we have set up these models for Basement Run, which is an ex-urban watershed, and to meet density suburb watershed, Stony Run, Scottsdale Branch, and a relatively urbanized watershed, Dead Run 5. And we are going to go through the results of the RISIS in the next few slides. So here we are just showing how RISIS can simulate the current condition of a watershed. Here we are building the watershed for Stony Run. It's just slightly north of the Johns Hopkins campus. On the left figure, that's the basin level discharge simulation on the top panel. You can see we reasonably capture the stream flow simulation at a daily scale compared to the USGS observation. And our RISIS model can also simulate the evapotranspiration reasonably, like in the early May when leaves start to grow and mature. We are estimating our ET simulation is increasing, and to the end of the growing season in October and November, the ET drops because the leaves fall down. There's no transpiration occur. And this gonna affect the groundwater table depths in the soil. As you can see, during the growing season, the groundwater table depth is increasing because all the trees are transpire the water in the soil. But when we enter the dormant season and when we have some storm events, we are start to recharge the watershed a little bit, so the groundwater table depth start to increase. And this is the left figure showing the average condition of the entire basin, but we can also go into each location of the watershed to see how the groundwater tables change over time, and what's gonna happen to the volumetric water contents, the soil moisture level here. So these two are kind of inversely related. So for the riparian areas we have here, the water table depth is generally low. And you can see here the soil moisture level here gonna be high. And the ET, GPP, they are basically highly correlated to each other. And we can see when in the watershed where we have a lot of trees, in the growing season, they start to, the GPP and the ET gonna be pretty high. And the RISIS model can be also used to evaluate the effectiveness of green infrastructures. So here we go to Scottsdale Branch. We examine some ecosystem restoration scenarios, specifically reforestation and roadside bioswale. So we're just going to zoom into this small area to see how we change the land cover. So on the left, the figure shows the current condition of land cover. So the light green, that's the grass, deep green, that's the forest, and the red dots are the individual buildings there. So for the reforestation scenario, we just converted all the lawns 10 meters away from the building to be forest. And as you can see, we converted the baseball field to be a forest here. And that's our reforestation scenario. And for the roadside as well, we just build like a 2-meter buffer that's really tiny, probably hard to see, along each side of the road. So we just want to see how this 2-meter buffer can intercept the runoff generated from the roads. And again, we here just comparing the change from the new green infrastructure scenarios comparing to the status quo. And here we can see when we have a more forest in the area, during the growing season, we make the watershed overall drier because we transpire more. And then in terms of the stream flow, we can effectively reduce the storm flow discharge in this dry period of the season when we reforest the watershed a lot. Besides of the change of water, we can also see the change of denitrification, these biogeochemical processes in every location in the watershed. So this can help us to identify how the nitrogen load is gonna change and where are the hotspots gonna be, how this green infrastructure is gonna affect the nutrient retention processes. And here, the denitrification increased along the roads of the basement run. That's because the bioswale there increased the soil moisture a little bit. And that's the condition favored for the denitrification rate. And for the, you probably can't see anything here because there's not much change for the nitrogen uptake when we build the roadside bioswale. But when we reforest the watershed a lot, you can see we increase nitrogen uptake a lot. Okay, so we can also evaluate the water quality for the urban watershed. Here we just have a showcase for the basement run. So basement runs are fully served by the septic systems, and all households there have the septic systems and the ground fertilization processes. And we just want to highlight that we include these modules in the RESIS model. And previously, if we don't consider the extra nitrogen loads from septic and the ground fertilization, this dark blue line, that's our original simulations for the nitrate concentration. But when we consider both inputs, we boosted the nitrate concentration to this red line, which is much more closer to our our weekly observation data. That's the blue star. Sorry, the blue star here. Yeah. Okay. Yeah, and that's basically the end of it. And we just want to improve our model, collect more data. Like let's share the data in the group. Thank you.
Now, question. Oh, Ava, you're there. I have to download Ava, right?
It should be in the downloads. Thank you.
Yeah, but things weren't, so I'm worried. And it's easy because it's right there. And it's fast. Now I got it. Be open.
You just click the mouse to your next.
I think so. Come on. Oh, okay, just gonna show it. All right, who's up next? What are we gonna do? The timekeeper is speaking.
Right, I know, gotta get us back on track. Pressure's on. Okay. Hi, I'm Ava. I'm a PhD student working with Antonia. I'm in the water team, but I'm also on the decision science team. So I'm gonna give an overview of my work across both. Okay, so my work focuses in Broadway East. You can see Broadway East there in the black outline, and that's within the Eager Park watershed primarily, which is there in blue.
And there are no rivers that run through here directly, so what we're focused on primarily is pluvial flooding, or when there's a large amount of rainfall on the impervious area, which causes ponding. And as Julia said, then you've got excess water choking the storm inlets and running into people's basements, which is really negative. So to address pluvial flooding, we've got multiple different types of adaptations. We've talked about green infrastructure at length, these presentations. There's also gray infrastructure adaptations, and there's educational and policy changes that can all be made. However, it's very difficult to know which solution to implement when you're looking at a system that has so much uncertainty. So within the Eager Park watershed, we've got many, many stakeholders who have multiple conflicting stormwater objectives and values. And then furthermore, all of those stakeholders have metrics that they define success with differently. On top of that, there's more complexity when you consider an uncertain climate future, as well as uncertain infrastructure condition as a result of age, and then deep social vulnerability and further complexity. So problems with this many interdependent and unknown and complicating factors are very difficult to solve and typically have no perfect solution. As I think Ben started this whole meeting by calling them wicked problems. And wicked problems can be addressed in part. I guess we can explore the solutions to wicked problems with robust decision making. So currently, this is still a work in progress, but currently my objectives for the Eager Park watershed are as follows. We're looking to minimize flooding depth within the watershed. We're also looking to minimize the total cost of adaptations that are implemented within the watershed to address flooding. We're hoping to maximize co-benefits that are met with the air quality, water quality, urban heat, all of the teams, and we want to maximize equity metrics across the watershed. So getting a little more into the decision analysis, this tool is a coupled simulation model and optimization tool. And the simulation model is EPA SWIM, or Stormwater Management Model. EPA SWIM is a typical rainfall runoff model. So our inputs look like rainfall, current infrastructure, other things that go into a hydraulic or hydrologic model. And then that gives us our flooding output, which is flood depth. And from there, we can calculate the other objectives that I mentioned earlier. The other part of this is the simulation model, which is done with the Borg multi-objective evolutionary algorithm. And we can get into what that does a little more in detail. So a multi-objective evolutionary algorithm typically does optimization across many objectives. Here, we're going to look at two, for example's sake. So if we're looking at flooding depth and total cost, then of course we want a solution that reduces flooding to zero and costs no money, but those are hard to come by. So the evolutionary algorithm helps us identify these set of solutions, which are all equally optimal solutions. And I call them equally optimal because a solution that improves performance, so going down the axis by X amount, also decreases performance in the other direction by Y amount. And each solution in the solution space has these trade-offs that we want to investigate. So in summary, the multi-objective evolutionary algorithm helps us understand the possible outcomes and explore the trade-offs between them. But then we have to consider, what if the inputs change? So under projected climate scenarios, precipitation may change in the future. If our model inputs change, of course, the results of the algorithm will then change, and we'll go from this blue set of identified possible outcomes to instead the red set of solutions, which would be equally optimal under the changed rainfall scenario. And we want to, of course, identify adaptations which are successful when we're considering a changed climate, and previously identified solutions may no longer be sufficient when the climate has changed. So also assessing the changes which caused that failure can help reveal system vulnerabilities which may exist. So once we've identified the set of robust adaptations, then we want to chart a path forward for how those get implemented into the watershed. And this is called an implementation pathway. So an adaptation pathway. And an adaptation pathway should be designed so that it is shifting to new constraints and conditions, like action B here obviously was terminated or determined to no longer be functioning. So you could shift to any of the other actions which were identified as part of the adaptation pathway. And this work is still in its preliminary phases, but we're hoping to develop a new adaptation pathway for flooding in the city of Baltimore. Okay, take questions. Yes.
Or is there a way to account for non-linear trade-offs, so like some solutions might be both, might be make a bigger deal and be cheaper?
Yes. Yes, so. Yes.
Related to that, like so something, some of them are maybe a single metric, but maybe it's not all equal, so like if something might be more expensive. If two things are the same cost, but one is more equipment and one is more labor, there's that trade-off, beneficial trade-offs for the labor one instead of going
Yes, that's a great question. That could absolutely be written in as an objective. It's not something I've considered right now, that scenario in particular, but that could absolutely be written in as an objective. And then the set of options, the slew of options between more labor and more equipment would all be explored, and you could identify whatever the community chooses to be most preferential. Yeah.
It does, it seems like a wicked problem.
It is.
So one of my questions is then, in terms of, in terms of the metrics that you're considering as like things that are desired.
Yes.
That makes sense. And, I was curious about how you're quantifying, so that you quantify metrics for co-benefits and for equity and things like that. So I was wondering if you could speak more about how you're considering doing that.
Yeah, so that's something I need to dig into a little more fully. Haven't selected exactly what will be those metrics yet, but you could imagine, like for equity metrics, mortality is often chosen for like the heat team. That would be something. Flooding is obviously lots of people die when they're caught in floods, so that could be one of the equity metrics that we're looking at. Co-benefits, I'm not entirely sure what we'll do yet, but temperature changes would certainly be one that that we'd be interested in looking at. Thank you.
Sure.
Yeah.
Yes, I have a question. You show a form, you show a graph whereby you explain if the not if the y of the y axis.
Yes.
Is the cost. So I just want to know how are you calculating that? What is the science behind that? What is the unit price of the flat rate? So
Oh, okay. That's a great question. Yes. Okay, so unit price, I could see why you would get unit price of flood depth from this plot, but I would explain it a little bit differently. So each one of these dots would be like, say this is implementing 1,000, 100,000 trees, and it would cost X amount. It's not necessarily, if this solution is implementing 100,000 trees, then it would reduce flood depth by X amount and cost Y amount. It's not necessarily, this line isn't necessarily relating cost to flooding depth. Does that make sense?
Yeah, I was just wondering, in terms of kind of that, like the different ways of measuring stuff, if you got new data, or got new ways of measuring, how we do this process and create output.
Great question. Process is designed to be totally iterative, designed to be entirely community engaged, start with the community, hear what they want, and then iterate on that with changes or preferences that they may voice. So, yeah, that's a really good question. I should have emphasized that. Thank you.
Thank you.
Can I give a shout out to Claire, because we couldn't do any
Yeah,
of this modeling
really.
without Claire getting the data from DPW.
It has been really,
All right. And last up is Ray. Oh, and Ray, question, do you want to share your screen?
Yeah, that'd be great if I could do that.
Yes, you can do that. I'm gonna stop the share.
Okay.
And last, Ray Najar, Penn State. Go for it.
Okay. On. Make sure you can see my screen. Are you seeing anything?
Yes, you've got to swap displays for us.
Okay. How's that?
That's it.
Okay, great. Thanks, everybody. I really appreciate being able to present remotely. I'm really sorry I can't be there. Looks like the meeting's a lot of fun. I know things happen in person that don't happen over Zoom, and I regret missing those, but I just couldn't manage it for some personal reasons. So appreciate it. So yeah, I'm going to talk about some of the data analysis we've been doing as part of this project that was proposed. That's exactly what we proposed. I'm working with Maria Herman here at Penn State. I think she's doing all the heavy lifting, all the analysis. She's a research scientist in my group. And we've been working pretty closely, mainly with Alice Volpita, but also her staff, Barbara Johnson, Sarah Holter, and Adriana DeLuca at Blue Water, Baltimore, who have basically collected all the data that I'm going to be showing. So we've heard some of the motivation for this sort of thing already in the session. You know, water quality is very degraded in Baltimore Harbor, which I'm using interchangeably with the Patapsco River Estuary. I hope that's okay. Correct me if that's not right. There are intense and sometimes toxic algal blooms, decreased water clarity, dangerously low concentrations of dissolved oxygen in bottom waters. This is caused mainly by excessive inputs from land of nitrogen, phosphorus, and sediment. So we sort of know all that. We also know that climate and land use change will probably change water quality in the future, and that we're going to need monitoring, data analysis, and modeling to establish links between water quality and various driving factors so that we can predict and help to mitigate such changes. So we're working in the data analysis space. It's basically what we could manage given the resources we had. And also, we learned in writing the proposal that there were a lot of unanalyzed data in Baltimore Harbor, and it's something we like to do. And so it was a good fit. So what we did was we met right away with the Blue Water Baltimore folks. And of course, we had consulted with them when we wrote the proposal. We've had several meetings with them over Zoom. We haven't managed to pull off an in-person meeting yet, but we will. And we learned from we kind of considered the Blue Water Baltimore folks as stakeholders. They're a nonprofit, by the way. Maybe some of you know of them, but they make great water quality measurements both in the watershed and in the harbor. And so we consider them as stakeholders, and we're interested in what they were interested in, and how could we help them, essentially. And from their point of view, what they really wanted to do is trend analysis, maybe with a little more sophistication than they had done in the past. And they measure a lot of things, and we looked at a lot of data with them. But really, the things that they were most interested in were Secchi depth, and I'll explain what that is briefly. But that's a water clarity metric. Chlorophyll, which is a metric of eutrophication. You've heard about that already. And then Enterococcus bacteria, which is kind of a public health threat metric. So that's what they were interested in. But we're oceanographers. We were interested in things too, and we wanted to learn about spatial variability, among other things, and other types of temporal variability as well. So that's sort of the background. And I'll just say what Secchi depth is for those that you don't know. It's one of the oldest water quality measurements. You basically drop a disc into the water, this disc here that you see, and until you can't see it anymore. And that's a measure of the water clarity. All right, so what are the data? It's really a wonderful data set. And they've been making measurements for more than 10 years in the watershed, but I'm only going to show the tidal stations here. There's 22 of them, and they've got a measurement since 2013. So we've analyzed the data of this 10-year period from 2013 to 2022. They're out there approximately monthly at each of these stations. Unfortunately, they don't sample in the cold weather months, but it's pretty good seasonal coverage, basically spring, summer, and fall, April and November. And they measure those three variables I mentioned, plus a lot of other things, by the way: temperature, salinity, oxygen, nutrients. So those are interesting, and we may get to those at some point. But I'm just going to be showing the Secchi depth, chlorophyll, and bacteria analyses here. So I'll give you an example of the sort of analysis we did. It's not very sophisticated. We're just starting with fairly standard kind of statistical analyses and just kind of looking at the data just to see, what are they telling us? And so here's an example from a station sort of in the center of the estuary, although closer to the inner harbor than the main stem bay. And this is the Secchi depth at this station over 10 years. And you can see there's quite a lot of variability. You can see some seasonality. It's a very high dynamic range. You know, the ratio of the highest to lowest measurements like a factor of 10. And then here are the annual averages. You can start to see some of the interannual variability a little. I shouldn't say annual, April to November averages. And you can see there's still quite a range just in the averages themselves, like a factor, not quite a factor of 2 variability. And so, and we did notice that the dry years stand out as being, at least at this station, fairly clear, and wet years as fairly opaque, turbid waters. And then there's some seasonality that we saw too. The water tends to be clearest in the fall and least clear in the middle of the summer. So, but we didn't see any long-term trend, and that was what they were interested in. I mean, it is a short time period. There's a lot of interannual variability, but that was something we consistently found. So to summarize that, we didn't find any long-term trends at any of the 22 stations for Secchi depth and chlorophyll that had p-values less than 0.05. So they were always generally quite large. And also another indication was that we had as many positive trends as negative trends. And we did see this large interannual variability. So now in contrast, the Enterococcus bacteria were pretty much declining at all of the stations, or 3/4 or more of the stations. 17 of the 22 showed declining trends, although the p-values were still fairly high. But I think we could say with a fair bit of confidence, and I think some of their own analyses and report cards show this as well, that and there's other indications from cleanup efforts that Enterococcus bacteria is declining in the harbor. So, when we saw this impact that looked like was related to stream flow, we decided to analyze some of the data in terms of salinity, which is kind of an integrator of flow. And so we did some regression analysis. That means the mean annual cycle was removed of Secchi depth and chlorophyll versus the salinity anomaly at each station. And what we found is that Secchi depth generally increases with salinity. Chlorophyll, it's not as clear, also generally increases with salinity. And so drier conditions are associated with higher Secchi depth. That was kind of expected. Lower flows would produce higher, more clearer water, but we also found higher chlorophyll. That was a bit unexpected. So I get into some of the nuances here in these last 2 points. The bottom line is we need to explore multiple drivers of water clarity, including things like suspended solids. So I think I'm running out of time here, so I'll quickly go through some of the spatial variability. Baltimore Harbor is really complicated in terms of the flow regime. So the salinity variability is not what you expect in an estuary where it's fresher here and saltier out here. You see a few fresh data points here for the long-term averages and some fresher water here. So you got fresh water coming in from the main stem bay, really from the Susquehanna River, as well as smaller flows from from rivers like Jones Falls and the Patapsco River. We saw that in the maps for Enterococcus showed a pretty clear trend of higher concentrations like in the inner harbor and lower concentrations out by the main stem bay. So that was a very clear signal. But Secchi depth and chlorophyll showed this really very complicated and nuanced pattern that I don't have time to get into. But this is something that we'd like to investigate a little bit more, understanding some of this structure. So to summarize, we did not find long-term trends in Secchi depth and chlorophyll, but there's a lot of interannual variability that's related in part to salinity. Enterococcus bacteria is declining at most stations. It decreases from the upper to the lower estuary, and spatial variability in Secchi depth and chlorophyll is complex and likely reflects impacts of sources with varying characteristics. Thanks very much.
Let's say we have time for 1 or 2 questions. Andy.
Ray, that was really interesting. Harry Wong was talking at the Stack Climate Modeling Workshop about his 3D model of the harbor, and I've seen some of the results that came out of that, and he was talking about the linkages he could see in the model between what was coming out of the Jones Falls and what was coming in from the main bay, and I'm curious whether you're going to try to integrate some of what's in his model, because that looks like a wonderful resource for trying
Yeah.
to find some of these complexities you're talking about.
Oh yeah, I totally agree. It's really great that he's doing this work, and he's been doing it. I mean, he's got quite a history. He's got a one thing we used in writing the proposal was a tech report he wrote many years ago where he showed his model captures this fairly complex circulation structure with water coming into the harbor at the surface and at the bottom and then leaving at mid depths. It's really quite rich. So I learned of his work. It's also with Jeremy Testa, who's a collaborator of mine. So yeah, we've had conversations with Jeremy about this modeling effort, and I look forward to working with Harry and Jeremy and Julia Moriarty, who's another person that's going to be doing modeling along similar lines with a different model, but should be addressing some similar problems.
Very good. Oh, one more from Larry, and then we're gonna have lunch.
Thanks, Ray. We have a long, detailed record of discharge, salinity, nutrients coming in from the Gwynns Falls. And that we could probably extend that to the other sites. Is there sufficient temporal sampling to pick up the effect of large storms on the results that you're getting? Or is it, so what's the sampling framework that Blue Water Baltimore has been doing? They haven't been following storms, I presume.
Right. Yeah. It's monthly at typically. So the only thing in the estuary where we could get at these, if I'm understanding you correctly, these shorter time scales would be some of the YSIs that they've got in the harbor. And it's not them, it's Maryland Department of the Environment has a few YSIs, not only in the inner harbor there, but at a few other sites. So we were aware of that. We didn't include it in the proposal because we just don't have the resources to attack that data set as well. But I think that's one where you might be able to see some short-term impacts.
Thank you very much, Ray.
Thank you. Take care, everyone.
Back at 2. Lunch break. Back at 2.